Hello everyone and welcome back. My name is Mr. Kowalt, and in this video I'm going to be going over collision theory, a model for reaction process. So let's get into this. So the first thing I'm going to do in this video is I'm going to go over the basics of what collision theory is and how it relates to reactions. So I'm going to use the following as an example. The example of an oxygen atom in the gas phase reacting with ozone O3 and then creating two molecules of oxygen gas. So let's get started on this. So first thing, what happens in a reaction? Well, the first you have my representation of these species. So I have my oxygen atom, my ozone, which is three oxygen atoms bonded together, and then I have two molecules of two oxygens bonded for each. So the first step is going to be that the reactants collide. There's got to be collision between the two things that are part of the reactants. So the reactants have to collide together. That's why it's called collision theory. So step one, reactants have to collide together. So here I have my oxygen atom speeding towards the ozone molecule, which is speeding towards the oxygen atom. So they're speeding towards each other. So the oxygen atom collides with the ozone molecule. What's going to happen at this point here is the collision is going to cause an OO bond to break in the ozone. So here you could see the depiction of what's going on during the collision. So here, the oxygen atom, as it gets closer during the collision, there's going to be a formation of a bond between the oxygen atom and one of the oxygen atoms in the molecule of ozone. So you get a formation of a bond here. This is going to supply some energy for the reaction. So some energy is released by the formation of this bond. Remember, so as things come together, the potential energy decreases. So you're losing potential energy, so that energy is released. And in this case, that energy is harnessed in part to allow for the breaking of this bond here. So you have a breaking of the bond between one of the oxygen atoms in ozone and the other oxygen atom. So in this molecule, you have this oxygen single bond being broken. And so this requires energy. Some of that energy that's required to break this bond is supplied by the formation of this bond. So this atom is creating or forming a bond between with this oxygen in the molecule. At the same time, this atom is starting to break the bond with this oxygen. So this bond is being formed while this bond is in the process of being broken. Therefore, the energy that is released during the formation of this bond is then used to help break the bond that requires energy here. So this bond here. So that's the first step. Step one, reactants collide, and then you have the formation of one bond while you're breaking another bond. And again, the breaking of the bond requires energy. Some of that energy is used from the release of energy that's being during the formation of this bond. Okay, so once this step is completed, you then have the formation of an activated complex, which is the next step. So stay tuned. Okay, so welcome back. So in the second step of this reaction, so reminder, this is the reaction we're looking at. So oxygen atom combines with or reacts with ozone molecule with three oxygens, and that's going to form two oxygen molecules. So in the first step, we saw that they have to collide together. Bonds are going to start to be formed. Bonds are going to start to break. So here we are again. So here's where we left off. So the oxygen atom, the single oxygen atom, is going to start to form a bond with the oxygen atom in the ozone molecule. This oxygen atom is going to start to form a bond here. At the same time, it's going to start to break the bond between the oxygen in the molecule itself. So this bond is starting to break, this bond is starting to form. So during this process, what's happening is as this is moving closer, so this oxygen is moving closer, so these two are moving closer together. They're going to start to attract each other more strongly, right? So the closer they get together, there's going to be more attractive forces. Again, the potential energy is decreasing in this case, right? Because they're getting closer together, and therefore energy is being released. So releasing more energy. At the same time, the bond between these two is getting weaker. They're getting farther apart, so they're going to separate farther, and therefore, as they're separating farther, the attraction decreases. So they're moving farther apart. The attraction between these two starts to decrease. The bond is starting to weaken. This bond is starting to strengthen, and therefore, less energy is needed for further separation. So as they're getting farther apart, the bond is getting weaker, the attractive force is getting weaker, and therefore less energy is needed to further separate them. Okay, so then as this process is happening, you get to a point where both bonds are equal in energy. So at this point here, the potential energy between the atoms here is going to be equal to the potential energy between the atoms here. So the bond making here, right? The bond making here supplies energy that is equal to the energy required for the breaking of the bond. So you get at this point here, you're at what is called the activated complex or the transition state. So you've got equality here. So the bond here that is being formed is in an equal state as the bond that's being broken. So you're kind of at a middle ground here. So this is called the formation of the activated complex. So here you have an activated complex where the bond being formed is equal to the bond that's being broken. So the energy being released here is going to be equal to the energy absorbed here. So now we're at kind of the most unstable part of this reaction. So this is the highest energy part during the reaction. So at this point, we have the potential energy is decreasing here. Potential energy is increasing here. So at this point here, we have the highest amount of highest energy, highest potential energy state. This is because it's the highest energy state, it's going to be the most unstable. So highly unstable here. So it can't stay here. It's not going to stay here. We'll see what happens in step 3. Okay, so the third and final step is the formation of product. At this point, we have the activated complex again. We have the bond breaking, or bond making is equal to the bond breaking. And so we're at the most unstable state, the highest energy state here. And so what's going to happen at this point is, as at some point during the reaction, beyond this point here, the bond making is going to predominate over the bond breaking. Bond making is going to predominate over bond making. So here we have the bond making. So this is going to be being made. So this is going to start to predominate and over this one. So this bond is going to be formed, and this bond is going to be broken. So you see that here, that this is the process. So this is getting to be closer together. This is going to start to form, and then this is going to start to break. Okay, or I shouldn't say start to break, but it's going further towards breaking. This is going further towards making. So at this point here, now the bond making is going to supply more energy in this case here. So remember, in this reaction, the formation of this bond is going to supply more energy than that's required or necessary for the breaking of this bond. So since this bond is releasing more energy than this bond needs to absorb to break, then you're going to end up with a surplus of energy, and that energy is released. So in this process, as the bond is being formed here, it's releasing energy. It's releasing more energy than is needed for this bond to be broken. This bond, as you're breaking this bond is absorbing some of that energy, but not all of that energy. And so therefore, some energy is left over, and you're going to experience that in the form of, say, heat, for example. So this is the formation of the products. And so those are the 3 steps. So remember, step 1, they're going to be colliding with each other. The reactants are colliding with each other. The bond is starting to form. This bond is starting to break. And then you get to the next step, which is the activated complex, where you're at the highest energy peak. You're at the most unstable point. The bonds being broken is equal to bonds being formed. And then after that, you start to go downhill, and you finally form the bond that takes over. So bond making predominates over bond breaking. You form new bonds, you break old bonds, and then you get your products. So, however, we need to talk a little bit more about how we got to this part here. So remember, when these molecules, or this atom and molecules, when these guys collide with each other, it takes a certain amount of energy to start to break bonds and to form the activated complex. That energy that is supplied is called the activation energy. The activation energy is the energy that's needed to get to the activated complex. So there's a certain amount of energy that is necessary to form the complex. That is called the activation energy, and I'll talk about that next, so stay tuned. Okay, let's talk about activation energy. So here, once again, we have our oxygen atom colliding with an ozone molecule to form 2 oxygen molecules. So as I was saying, in order to form that activated complex or transition state, you need to get over a certain amount of energy to do that. So a certain amount of energy is needed in order to reach that activated state, or the transition state. So I want to use an analogy of a ball rolling up a hill. So here I have a ball rolling up a hill. In order to get the ball to roll over to the other side of the hill, I need to supply the ball with enough energy to reach, at the very least, the top of the hill. If I don't put in enough energy, the ball will roll up to a certain height, and then it'll roll back down. And so it won't go over the hill and reach the other side and go down the other side. So just as I need enough energy to get it up here, once it gets up here and starts to roll down, no more energy is needed because the gravity will take place. So the potential energy at this point will automatically start to form and convert to kinetic energy by the act of gravity. So, but in order to get it to this point, I need to supply enough energy so that the ball can get to there and then roll down on its own, right? On its own, with gravity. So this is analogous to activation energy. So all reactions have a certain amount of energy that's needed to overcome in order to get the reaction to go. So if you don't supply the reaction with enough energy to reach the activation energy, to overcome this activation energy, the reaction will not happen. So in this case here, we're talking about reactants that are moving at a certain speed. They have enough kinetic energy. They collide with a certain force. So the motion of these molecules, of these reactants, the energy here that they collide with has to be enough to give enough energy to supply that energy, or supply enough energy to overcome the activation energy. So if the two reactants are not colliding, so this ozone molecule is going this way, this oxygen atom is going this way, they have to be moving with enough speed and enough energy such that when they collide, they'll form products. They'll get to that activation state, or that activating complex, or active complex, or the transition state. So in this case, just as the ball doesn't have enough energy to get to the top, it rolls back down. In this case, these two do not have enough energy such that when they collide, they're not going to form the activated complex. They're not going to form that transition state. So you'll get a bond here that might start to form, and you'll get this bond here to start to break, but it's just not enough to get the full formation of the bond and the full breaking of this bond. So what ends up happening is that they just go back to where they were. So just as the ball goes up to a certain height, it rolls back down. In this case, you might get a partial bond being broken, a partial bond being formed, but it's not enough to break the bond fully, to form the bond fully. So then they end up just ricocheting off of each other. So the atom goes back, so it ricochets. The molecule stays, it goes in the opposite directions. So they kind of just bounce off each other without forming any products. Okay, so but if you can supply, if the molecule, if these reactants have enough energy when they collide, then it's like the ball that has enough energy that goes to the top and then is now to overcome the activation energy. Now it's able to roll it down the hill on its own, right? So no more energy is needed. No more energy is needed to supply. At this point, it'll just roll down the hill. So in the same way, if these have enough energy when they collide, then it'll be enough to reach the activated complex. It'll be enough to reach that transition state. And then at that point, the bond that's being formed can fully form, and the bond that's being broken can be fully broken to form products. So that's what you see here. So you have the ozone molecule here. You have the oxygen atom. They're colliding with each other. This bond can form now. This can form a bond. This will break the bond. You'll get the activated complex. And then it'll keep going until now you've got the two molecules of oxygen formed. So now this bond is completely formed to form this oxygen molecule, and then this bond is completely broken to form this oxygen molecule. So this is an example of where the activated complex is formed, where you've added enough energy to overcome the activation energy. Here, not enough energy is supplied, so you're unable to overcome the activation energy, so no products are formed. So now what I want to do is I want to show this in terms of energy diagrams. So let's go over energy diagrams. Okay, let's talk about energy diagrams. So I've talked about overcoming the activation energy in order to form products. So we're going to represent these in terms of what is called an energy diagram. So I know there's a lot here, so let me just go through it step by step. So here, as we said, we're having oxygen atom react with ozone molecule to form two oxygen molecules. So here we have the energy of just the oxygen and the ozone molecule. So here's my oxygen atom, here's my ozone molecule, and this is the energy before the reaction. So at this level right here, that's the level of the energy we're at, okay? So as they come together and they collide, again, at this point, as you're coming together, you're going to be forming a bond, you're going to be breaking a bond. So at this point, the energy is going up, right? So the amount of energy, the potential energy is increasing during this process here of forming and breaking bonds. So in this process here, we're in the process of bond breaking predominance. So here, during this part here, the bonds being broken or bond breaking is the predominant thing that's going on at this point here. And so at this point, energy is being absorbed because you're breaking a bond. This relates to the activation energy. So here's the activation energy. We've got to come and we've got to get to this point where we're now forming the activated complex. So at this point, we're equally forming as well as equally breaking bonds. So the energy is at its highest point here. This is the most stable state. If the two colliding reactants have enough energy to overcome this activation energy and form the activated complex, then it's all downhill from there. So then now, at this point, you've overcome the activation energy. And so now, at this point here, bond making predominant. So now the predominant thing is bond making. And so energy is being released. And so you can see that you're going down, down, down. So you're forming the bond, you're breaking the bond. So you're making the bond here. So that's going to predominate. So when you're making a bond, you're releasing energy. It's going down in energy until this bond is fully formed, this bond is fully broken, and you've got your two products. So you've got your two ozone molecules. And so you end up with an energy down here after the reaction. So this is the energy after the reaction. This is the energy before the reaction. So notice that the products here have a lower energy compared to the reactants. So energy was lost. Why? Because more energy was released during the making of the bond than energy absorbed, right, during the making of the bond, or so during the making of the bond, right? So breaking of the bond, excuse me. So this is absorbing energy, this is releasing energy. So when you end up with reactants that are higher in energy compared to the products, if the products are lower energy compared to the reactants, then you have an overall release of energy. So this means that this is lower than this. So you have an overall release of energy. And this here, if you look at this distance here, this is the overall energy that's released. So overall energy released between reactants and products. And so therefore, we call this an exergonic reaction. Exer meaning out, gonic referring to energy. So it's a reaction where energy is released out. So exergonic reaction, reactants have a higher energy than the products. Products end up with a lower energy because overall, during the reaction, energy is released. And so, therefore, exergonic reaction. Well, what if it's the opposite? So we see that the formation of two oxygen molecules from ozone and an oxygen atom results in the release of energy. It's an exergonic reaction. What if it's an opposite, right? So here we have A plus BC. I have a molecule BC. I have A, some atom. And again, here's the activation energy. So these two reactants, these two reactants have to be supplied with enough energy that when they collide, they will overcome the reactivation energy. So here you can see that the activation energy here is much larger. Let me fix this. And so they have to overcome this energy. So again, here, the bond breaking predominates. So in this case, it takes a lot more energy to break bonds to get to the activation energy. So here, now that you're at the activated complex, now you can go downhill. This is where the bond making predominates. So bond making, remember, releases energy. So look at the amount of energy that is needed to be absorbed during the bond breaking process relative to the bond making process. So more energy is needed to break bonds than energy released in the making of bonds. So in this case, the energy of the reactants is lower than the energy of the products. So the products have a higher energy than the reactants. You have more energy than you started with. This means that overall energy was absorbed. So look at the difference in energy here. So if I bring this over here, right, you can see here the overall amount of energy that was absorbed. So I started here with the reactants at this level, and I end up at this level with the products. Products have more energy. Energy was absorbed. So this is an endergonic reaction. Ender meaning into, so energy going into during the reaction. So it's absorbing energy. So this is an energy diagram showing that you have an endergonic reaction. So anytime your products end up with more energy than the reactants, that means energy was absorbed. You have an endergonic reaction. Anytime you have products that are lower in energy than the reactants you started with, then that means energy was released, energy was lost. So that means that you have an exergonic reaction. Okay, so this is a good introduction into energy diagrams. The last thing I want to talk about is the excuse me, the orientation of the molecules. Okay, ladies and gentlemen, so the last thing I want to talk about is orientation. Orientation. So I said that for according to collision theory, in order for a reaction to happen, they have to collide with the right amount of energy to form the activated complex to overcome that activation energy. But they also need to have the right orientation. They need to have the right orientation to form the activated complex so that the bonds that need to be formed are being formed and the bonds that need to break are being broken. So here's an example. So here, if I have my oxygen atom colliding this way with the ozone molecule, the bond between this atom and this one can form, while the bond between these two can break. However, for this one, this would be unfavorable because notice that the direction or orientation that they are colliding, this oxygen atom is colliding with this oxygen atom. And so in this case, you'll try to form a bond here, but then again, here it's not going to be breaking the right bond. So here we're not forming the right bond. And then here we have two bonds we would need to break, and then these would have to form. So this is not the right orientation. So in this case, it wouldn't be favorable. So you need the right amount of energy, you need the right orientation. So here's a summary. So for summary of collision theory, reactant particles must collide. That's number one. Number two, the collisions must provide at least the minimum energy needed to produce the activated complex. So activation energy, you need to have the activation energy. And three, the orientation of the collided particles must favor the formation of the activated complex in which new bonds are being formed and the old bonds are breaking. That's it for this video. I hope you enjoyed this video. If you like this video, please hit that like button, subscribe to my channel, hit that notification bell, put a comment down below, let me know what you think, And thanks for joining me. Have a great day.